Okay, now this is a bit of a lash up of the stepper motor, the motor driver, my numerically controlled oscillator circuit, and the power supply that came with the kit, 60 volt 6 amp power supply, and I've got a bench power supply that's simulating the enable signal and the direction signal, and the pulses for the speed come from my numerically controlled oscillator. Okay, pick out the bits. This is the big stepper motor. I've just put a pulley on the front there so we can see the shaft turning easier. I put a mark on the pulley. The interface to this is a thick cable that goes into the controller. There's only 4 wires inside there. There's two windings in the stepper motor that you have to connect, and that connects, this black lead here connects into the left hand connector block, and as you can see there's A plus A minus, B plus B minus. They're the 2 coils in the stepper, and then VCC and ground, that's the high voltage 60 volts DC signal from the power supply, which is this little beast. The mains driven 240 volts, and the 2 wires here you see, they're the wires going off to the stepper motor controller. The power supply's got a little fan in it to keep it cool. It needs to be blowing outwards. The other parts are, this is my test board with the microcontroller chip, which is the black device in the middle. The LED that's flashing, that's just telling me that this is going to change in the next iteration. But that LED, all that's doing is indicating every single interrupt. I've got it interrupt driven for accurate timing. The little red switches here, the top 2 are the gearbox. There's a high and a low setting, and there's 4 gears you can get from 2 switches, and the lowest switch is the fast, simulates the fast rotation mode, fixed fast speed, that is just for whizzing the mill deck left and right fast. Now the ratios of the pulses can be altered, as I've said. On this board there is a little DC regulator that goes from the 12 volts that this runs from down to 5 volts to run the chip. I'm running at the moment off of some lithium ion batteries, which gives me 12 volts roughly, 4.2 each when they're fully charged. My bench power supply, as I said earlier, simulates the right hand side here, this switch, that simulates the direction, and the left one here will simulate the enable on and off. So that would be generated normally by the overall user control panel when you're switching the X feed on and off. Okay, now then, let me see. We're connected up, so the power supply here is connected to the mains. My test board is connected to my battery pack, and then the 2 wires that really matter, which is the drive, goes from this terminal block at the end here and connects into the signal areas. As you can see, you've got direction that comes from my power supply, pulse comes from the numerically controlled oscillator there, and the enable at the moment comes from my simulated power supply over there. At the moment I've got it disabled, so if I turn that on, at the moment we're very slow. Now this This is the pot here, simulates the control panel potentiometer for varying the speed. You might be able to just hear that. So wind that up, and there she goes. She's rotating quite nicely, very smoothly actually. You wouldn't know that there are little micro steps in between each one, so it's actually effectively stopping and starting, but very quickly. It's continuous though. And if I operate the direction, you will see it immediately goes in the opposite direction just by the flick of this switch up here. Down, goes that way, anti-clockwise, the other way, clockwise. And then the enable disable switch over here will stop it dead, and when I enable it, click, off she goes again. Stop, go. Bit of a delay, that's because there's a bit of capacitance in the line. That will go when it's on the proper control circuit. Right, so let's have a play with the speed. Hard to do this with one hand. Right, I'm on the fastest. You can hear that going. There are resonances within the speed range. Right, that's the maximum pot speed on the highest gear at the moment. And as I wind that down, right the way down. It's virtually stopped, but it is actually moving because it's going about 1 pulse per second. You can hear that ticking. That would take 3,200 pulses to do one complete revolution. That's because of the micro stepping. Now if I can simulate, say for instance we were running at this speed, just wind the pot up a bit, and we wanted to whiz the bed of the mill fast, we would operate this. I'm going to operate the high speed mode with that little switch on there. It immediately goes into the fast rotation. Take the fast off, which would be simulating you taking your finger off the high speed, and we're back to the pot controlled speed. There you go, that's it. All the bits seem to work. So it was a good little test bed. The next bit is to get all the control panel switches and things together so we can see the whole of the software working, which isn't written yet, but shouldn't take too long. Signing out.